So here we're going to talk about the mean, median, mode, and then what an outlier is. So the first definition we got is a mean of a data set is the sum of the data entries divided by the number of entries. Okay. So we've got population mean, which is represented by mu, pronounced mu. So it's mu, so Greek alphabet letter, is equal to the sum of all the data points, x, divided by the total number in the entire population. So this is the number of entries in the population. Okay. And then we've also got the sample mean, which is calculated mathematically the same. It's denoted by x bar, so you say x bar, and this is equal to the sum of the data entries in the sample divided by lowercase n, where the lowercase n stands for the number of entries in the sample versus the population for the above mu here. Okay, so two different things, but mathematically they are equivalent. This is what's known as an unbiased estimator. Okay, x bar is an unbiased estimator for mu, since mathematically there's no bias there. All right, so let's take an example and find the mean. So take an example of test scores 60, 72, 93, and 90. And what am I going to do? To get the population mean, I add up all the data entries and I divide by how many there are. So that's 60 plus 72 plus 93 plus 90, all divided by how many there are. There's 4 total. And so what do I get? I get 315 divided by 4, which happens to be 78.75. So that is the mean, right? Not too difficult. So if it tells you population mean, then you use the first formula. If it says sample mean, then you use the second formula. But they're going to produce the same thing. Only one is going to say mu equals that, and the other one's going to say x bar equals 78.75. Okay, that's the only difference. X bar is a sample statistic, and mu is a population parameter. All right, let's talk about the median. The median, okay, and by the way, the mean always exists. Always exists. We can always get a mean. If you give me a list of numbers, I can find an average. The median always exists too. Always exists. Okay, so the median of a data set is the value that lies in the middle of the data when the data set is ordered. Okay. So we'll take a data set here. Example 1, 5, 18, 30, and then 30 again. Okay. This one already in order for us. Okay, it's already in order. So first thing I would do, step 1, is order least to greatest. Well, it's already done for us here. So now that I've ordered it from least to greatest, pick the one that lies in the middle. What lies in the middle? Well, there are 1, 2, 3, 4, 5. So there's n equal to 5 data points. So I just look and I see, okay, 18 looks like it's the one that's in the middle. There's 2 on the left, 2 on the right. So yeah, 18's in the middle. So the median is equal to 18. Now there's a trick here to get the median. The median is equal to n plus 1 divided by 2. Okay? So it's n plus 1 divided by 2. So n is how many there are. There were 5, so that's 5 plus 1 divided by 2. That's 6 over 2, which is 3. Now what does the 3 tell me? That tells me that I'm looking at the first, second, third number. So the third number is my median. Okay, so that's why it lines up like it does here. Okay, so the third number is the median. All right, let's do another example. So say instead of having some odd n, let's do it where it's like 2, 17, 12, 13, 18, 21. Okay, what's the first step that we do? First thing we do is we order from least to greatest. So the least looks like 2, so I'm going to mark 2 out. The next one looks like 12, then 13, then 17, then 18, then 21. Now I go and I look for the middle one. Well, there's 1, 2, 3, 4, 5, 6. So there's n equal to 6. Okay, so if I pick 13, well, there's 2 over here and there's 3 over here. So that's not in the middle. If I pick 17, there's 3 over here and then there's 2 over there. So that's not in the middle. So I've got a problem here. Okay, it seems like it would be somewhere between those two because look, there's 3 here and there's 3 over there, right? So if I plug this into my formula, I get n plus 1 over 2 gives me 6 plus 1 over 2, which is 7 over 2, which is 3.5. Well, 3.5 isn't a position, but what is it? It's halfway between position 3 and position 4. Position 3 and position 4 here. Halfway in between those two. So what do? I take 13 and 17 and I average them. 13 plus 17 divided by 2. So 13 and 17, that's 30. Divided by 2, that's 15. So my median is 15. Okay, so that's the oddball when you've got an even n. So n is even, then you've got to split it down the middle, and your median is actually a number that's not in the data set. So the median here is equal to 15. Okay, so it is possible to have a median that is not a original data point. Just like it's possible to have an average of 78.5 that wasn't one of the original test scores. Okay? So that's the weird case. Now, the next scenario is the mode. The mode sometimes exists. Sometimes there's no mode. Okay? So sometimes you can have no mode. You can always have a median. You can always find a median. You can always find a mean. But sometimes there's just no mode. And so mode of a data set is the entry that occurs with greatest frequency. Okay? The entry that occurs with greatest frequency. Now, say I have 3 examples. 1, 2, 3. 1, 1, 2, 3. And 1, 2, 2, 3, 3, 5. Okay? For this first data set, there's 1, 1, there's 1, 2, and 1, 3. Is there any number that occurs with the greatest frequency? No, they all occur with exactly 1. So that tells me that there is no mode. When none of them occur more than the other, okay, and they all occur exactly 1 time, then there's no mode, okay? The next one, okay, mode is the one that occurs the most. So there's 2 of those 1s. There's 1, 2, and 1, 3. So the mode here is equal to 1. 1 occurs twice, okay? Now this last one here, it looks like 1 occurs 1 time, 2 occurs twice, 3 occurs twice, and then 5 occurs once, okay? So looks like we've got 2 numbers that occur with the same amount of frequency. So we call this bimodal. Bimodal means there's 2 modes, okay? So there's a mode that equals 2 and a mode that equals 3. Okay, so here's a mode and here's a mode. All right? Now, the last concept in this video is the outlier. Outlier is a data entry that is far removed from the other entries in the data set. Okay? Now, say you've got a dot plot and you've got a bunch of dots over here. And then you got a dot way over here. There's a big gap between all the data points here and then this one lonely data point over there. This would be an example of an outlier. Okay, so it's not a very mathematical definition here. We're just saying, look, if it's really far away, then that's a huge outlier, right? So the way I think about outliers, I think about, like, say we were going to find the average of all the people who were inside a bar, what their salary was. Okay, so all these people are in a bar. Okay, and so maybe the average salary in this bar is $50,000 annual salary. Okay, well then all of a sudden Bill Gates walks into the bar. Okay, and Bill Gates, worth a little bit of money. Maybe he makes $1 billion per year. Okay, so that average salary, $1 billion per year. Okay, now what's going to happen to the average? The new average, including Bill Gates, is now, well, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 people who make $50,000. So what would that be? That'd be 11 times 50,000. Okay, so that's 550,000. That's a good amount of money. But if I add $1 billion, so that's 1, 2, 3, 1, 2, 3, 1, 2, 3, enter. So that's 12 people. So I divide by 12. And so that would be 833,791. So 833,791. And then 66. So that means now the average amount of money that everyone makes in that bar is $83,379,166. Well, guess what, guys? Nobody makes near 83 million if they're all these people are averaging 50K, right? So the outliers can greatly affect the average. Okay, so the outlier affects the mean. Okay, the outlier has a great effect on the mean. All right, and you just think about the Bill Gates example. He took all those people who averaged 50,000 and made it look like now the true average was 83 million, which is ridiculous. Only Bill Gates is the rich one in that bar, guys. Everybody else is just, average. Okay, so that's the idea of how the outlier will potentially skew the mean, and why when you're talking about salaries at a company, it's really better to know the median salary. That way, the fat cat CEO who's making all the money, it's not like, oh look, come work for us and the average salary here is 83 million, right? Well, is the average salary 83 million? Yeah, I mean, technically speaking, it is 83 million, but nobody makes 83 million. Everybody makes in this 50,000 range, and then, this one person here makes a billion. Okay, so kind of a extreme scenario there, but I did that just to illustrate the point.